particularly the ores and the soil. So in that case, whatever if you want to say, so this particular thing will be applied in case of ores as well as in soil. So this is the that is best method of this one. So in this method, we have to understand that what is the objective of this differential thermal analysis. The objective is to make the students aware about the thermo-analytical techniques. Okay, so DTA, that is the important of DTA, that is thermo-analytical techniques. So which is essential for all of your that is areas and that study and all the things. Then what the outcome that is after studying of this differential thermal analysis, what is the outcome of this one? To make students that is after completion of this topic, students would be able to understand the principles and the application of a thermoanalytical techniques in a drug analysis. Usually what I'm saying, it is a drug analysis, not only the drug analysis, it is that is materially associated with that your temperature associated with this particular that is ores, and also in case of solid substances like your soil, and this is drugs also, that medical pharmaceutical industries. So it is used. Okay, let's go to the next slide and try to understand this one. Okay, so what is this? This is contain one reference electrode, one that is sample also, that is it contains one thermocouples is essential, furnace is natural temperature, for the temperature furnace is there, sample temperature you have to take, and temperature difference you have to take it. We'll go to each and everything. Okay, now differential thermal analysis, DTA. So what is the principle? What is the principle behind this? Okay, the basic principle behind this, is the involved in DTA is the temperature difference. So change in temperature, initial temperature, or what is the temperature, and final what is the temperature, and what is the change in temperature. Suppose the initial temperature is 20 degree and the final temperature is 50 degrees Celsius. So what is the difference? Change in temperature is 30 degrees. Also that is the point between the test sample and inert reference sample. As you see that two samples we are using here. So one is the reference and another is sample. Okay, so reference with his test sample. This is two things are there. So you have to that is what is factors are associated with the test sample, and this between that two things, what is the difference of change in temperature is we are studying. So that fact we have to note it down. Under control and identical condition, as you see that control condition means, if you go to that previous slide, you will see control means this is furnace control. Thermocouple means its temperature should be controlled, right? Temperature should be controlled, thermocouple. Okay, so and the thing is that here that is condition is heating or cooling is recorded. So when the temperature is there, so that the substance, what is the nature of the substance, you have to note it down. But is the how that is, whether it is that the temperature is rise in case of the same sample, or it is decreases in that case of sample. But just I told you the one example I gave you. So if initial temperature is 20 degree, but after the when you are passing through this temperature, change in temperature is 50 degrees, so difference is 30 degree of that one. So that should be calculated. Maybe temperature increases or maybe temperature decreases, that does not matter, but change in temperature you have to that is it, you have to identify. Under control and identical condition of heating or cooling is recorded continuously as a function of the temperature within or time. Okay, so it is a graph. You have to represent the graph. On the basis of that, you have to calculate whether that temperature is increases or decreases with increase in temperature as well as time. So thus the heat is absorbed or emitted. See that it is depends upon the substance, that whether that temperature will be absorbed by the substance or it is emitted by the substance. So that is depending upon it, because as you know that so many chemical reactions are there, as I including this. So the endothermic reactions are there, and the exothermic reactions are there. So it is depending upon the situation whether that is absorbed or emitted, that temperature by the chemical system determined. Okay, what chemical system you are using for what that chemical compound you are using. So that chemical compound, whether they absorb the temperature or emit the temperature, that depending upon the situation. So that is the principle of this one. Okay, next we will go down that if any reaction takes place in the sample. Okay, so if any reaction takes place in the sample, then the temperature difference will occurs between the sample as well as the reference material. So when we provide the temperature, so if the temperature that is then the when you provide the temperature, both the electrodes, both the sample as well as the reference electrode. Okay, if reaction takes place in the sample, so when that is, reaction takes place, so if you provide the temperature, the reaction takes place, and the kinetic energy will be increases. So that means the temperature will be temperature will increases. Okay, so or decreases, whatever. Then the temperature difference will occurs between the sample as well as the reference material. So in the second condition, in an endothermic change, such as melting or dehydration of the sample. So endothermic change, that in the endothermic, as I told, the exothermic and endothermic reaction. This endothermic reaction means temperature is observed, right? Not okay. In the chemical reaction, temperature is lowest temperature is released, temperature is observed. It is not the matter that a temperature, not a single bit of temperature is observed, or single bit of temperature is, but on the basis of the how much temperature is observed, how much temperature is released. On the basis of that, we can say that whether it is an endothermic reaction or exothermic reaction. If the temperature that is after the calculation, if you see the amount of temperature is provided when that is giving or supporting to the chemical reaction is more than the amount of temperature increase that released, so that means it is endothermic reaction. Otherwise, you can say if that amount of temperature released is higher than that of your that is amount of temperature you are providing, that is endothermic. Sorry, exothermic. So in that, the temperature of the sample is lower than that of the reference material. So del T is minus that is negative. Okay, so it is endothermic reaction. In an exothermic change of the process, the sample temperature is higher than that of a reference material. So that I told you, explain, that is written here. So del T is equal to positive. If del T is negative, so that is that is sample temperature is lower than the reference temperature. Okay, sample temperature lower than the reference temperature, then del T is equal to negative, so it is endothermic. If sample temperature higher than the reference, so it is that is exothermic, that is reaction. Okay, so next, then the shape of the size of the peak. So this is the thing. If you see the graph, so the shape of the size of the peak gives the information about the nature of the test sample. Sharp endothermic peaks indicates phase changes. See, that is this sample has the that is you see that a sharp edge is there to the bottom part of that, a sharp edge is there. So that means it is giving that, it is telling that it is peak. It is means straight the change in the temperature. Okay, that means the melting point, fusion, that is fusion and all the things, the transition from the crystalline form to another crystalline form. So that is completely straight. If this straight that is a sharp edge is providing, so this is, you can say, this is completely, what is that, endothermic reaction. So okay, broad endothermic peaks obtained means this is the endothermic reaction, but it is broad end, means but that is a little bit flat, means hypobola, so that is surface edge peak is there. So that is broad, that is a broad endothermic peak are obtained from the dehydration reaction. So chemical reactions that is like oxidation, the oxidative and oxidative reaction as are exothermic reaction. So this is on the basis of that. Okay, next we will come down to the next slide. So what is the instrumentation of that is DTA block diagrams, right? So the DTA apparatus consisting of following components, that a furnace sample and a reference holder with a thermocouple assemble, right? So thermocouple, you see that picture, this furnace is there. So sample holder furnace to heat the sample, and then furnace temperature controller to increase the furnace temperature steadily. Then the furnace atmospheric controls, it is mentioned over there in that diagram. Okay, so that is atmospheric control system to maintain the suitable atmosphere in the furnace of sample holders. Next, recording device, you have to record it definitely. So differential temperature sensor, so what is the change in the temperature is there, so that means that sensor should be there. to measure the temperature difference between the sample and the reference materials. The sample and the reference holder are kept inside the furnace, because you have to provide the temperature to both the sample as well as to the reference electrode. So furnace and the temperature of the furnace and a sample holder are controlled by using the furnace controller. So temperatures, see that if it is a furnace, so temperature may be highly increased at the time. So we have to control the system. Temperature medium should be 100 20 30 whatever may be, that you fix the point, that one on the basis of 20 degree what is the behavior, 30 degree what is the behavior, 40 degree what is the behavior. So when the behavior changes, that is endothermic. In the suppose that in one system, then the initial condition 20 degree, it will be the endothermic, but 40 degree it will be the exothermic. So maybe that probability that you have to see, and you have to understand about that things also. So DTA of a calcium oxalate monohydrate. A simple thing is here, that is I am giving an example. See, here is a water molecule, monohydrate. So DTA calcium oxalate, then monohydrate, means oxalic acid is there, calcium is there, right? Oxalate means it's coming from the oxalic acid. So COOH, bond COH means C2O4H2 is the oxalic acid. So okay, if you remove one that is hydrogen or two hydrogen, whatever may be, so that will be come under the oxalate, means COO minus, then COO minus. Okay, this is the oxalate, single minus or double minus, that is not the issue. Then monohydrate means single water molecule is present, H2O single molecule. So water molecules is present here. Okay, that is the most important, that we have discussed over there. So DTA curve of the decomposition of a calcium oxalate monohydrate is shown in the diagram. See, then the first B, it is that in the both the graph, you can say below one is the A and below above one is the B. Okay, in the A and B, when in the A and B you are thinking in presence of a carbon dioxide, so that is carbon dioxide in presence of, we are doing that experiment. So see that a peak, what is the behavior of this graph? Okay, and in case of air means mixed, that is particles should be there. So in that case, see that how the peaks of this particular graph that is going on. Okay, so this the thermogram shows the decomposition in carbon dioxide atmosphere and in air atmosphere. Both the two things are there, one in the carbon dioxide, second in the air, in place of air. So let's study that on. So DTA of a calcium oxalate monohydrate. So first thing, that is the thermogram, means the graph of a calcium oxalate monohydrate has three peaks. In the first case, you will see that is three peaks. Sorry, yes, in the bit A, you will see three peaks. Left one and the middle one is the small one, and the end one is the large one also. So three peaks, and also in the upper part there is three peaks. But in the upper B, you will see that in the bit A, you will see that three peaks are towards the downwards. It's going downward. Three peaks are formed towards the downward. But in case of B, you will see that the middle peaks is upward direction, and the first one and last one out of three, first one and last one is downward, and that middle one is upper one. But in case of A, when the carbon dioxide is providing there, so that is all the three peaks are downwards. Let's understand that thing. So that monohydrate has three peaks corresponding to the successive elimination of H2O, carbon monoxide, and carbon dioxide. These 3 points of weight loss corresponds to the three endothermic process. So these three peaks are showing the endothermic, because the surface area is peak. Okay, that surface area is in peak condition in surface. So curve B represents the DTA diagram for the same compound in air. Same compound means calcium oxalate monohydrate, but in presence of air. The second peak curve is sharply exothermic. So it is the upward direction. Okay, now you understand. So if the peaks are in downward condition, that is endothermic, and if the peak are in upward condition, that is your exothermic nature. So in the second B condition, that is peak is in upward condition, that means sharp exothermic, but corresponds to the same weight loss of a carbon dioxide atmosphere. Okay. Now, this peak represents the exothermic burning of carbon monoxide in air at the temperature in the furnace. So it means that why it is that is exothermic, because here the carbon monoxide which is formed when the calcium oxalate monohydrate you will undergoes decomposition. So that is, water molecule will be removed, carbon monoxide will be formed, and carbon dioxide. When the carbon monoxide will be formed, that will be again in the air, it will changes to the carbon dioxide. So that is why it is, when carbon monoxide and carbon dioxide, as you know that carbon monoxide is more stable than the carbon dioxide. Carbon dioxide having the resonating formation, a resonating structure, but carbon monoxide is triple bond is there, so one dative bond is there. So triple bond is, it is around 10,000 degrees Celsius, that is stable structure. So that's why when it will undergoes for the oxidation in place of that is your furnace, so that is undergoes the oxidation and forms the carbon dioxide. Once carbon dioxide means high amount of that is means it contains the a vast amount of energy, carbon monoxide. When it will convert to the that is your carbon dioxide, it will go to another structure, but it has comparatively less energy, which is held by the carbon that is your dioxide. So hence release of energy is there. That's why it is forms the exothermic in nature. So that's why it is exothermic in nature. Okay. Then factors affecting DTA curve, instrumental factors. So size and shape of the sample and the furnace. What that is the instrument factors. If you will take that, just a second. So if you see that that is sample size and also the furnace holder size is also, that is important thing, that is calculation factor. Material from which sample holder is made and its corrosive attack. So from which that sample you are preparing, that is that material also, that is important. Heating rate, furnace heating rate also, that is the instrumental factors. Again the sample characteristics. So amount of the sample, as you know that MCH-1, several times I told you that a quantity of a sample is most important. How much amount of a sample you are taking, whether it is if you are taking the huge amount of a sample, the reaction time will be more, and it will be consumption of energy and all the things. So particle size of the sample, again that particle size, what is the size and the nature of the particles, that is also important. Next we will come down application of a DTA. Okay, so application of a DTA is that DTA curves for two substances are not identical. So it is two curves, that is two substance. When you are taking the reference as well as sample, so that curve is not always equal. If you take the, in case of here we have taken that what is calcium oxalate monohydrate. If you take the calcium oxalate dihydrate, if you take any kind of substance, so that that looks like the, that is what is the DNA fingerprinting, right? So it is the curve is always different to different that is substances. It is not no two that substance can give a single type of a curve. So curve always different to different. It is just like our fingerprint, DNA fingerprinting. Okay, so that hence they serve as a fingerprint of a various substances. That's I told you. So I am using that word. So this is your DNA fingerprinting. So our fingerprint is not equal to any that is, it is very particular to a very particular person. So that's why that this is just like a DNA fingerprinting. Okay, so used to study the characteristic of polymeric material. So polymeric material means any material contains that different types of that is elements, like your calcium oxalate and what is water. So that is carbon, hydrogen, oxygen, all are there. Okay, and different compounds is oxalic acid is there, calcium is there, water is there. So different bond nature having there also. So these are called known as the polymeric material. Otherwise, you can say that any ore, if you take the ore, okay. Yesterday also we are discussing about the ore. In a particular graph, you can understand that is whether it is calcium, that is potassium, magnesium. What are the different zinc, that is lead. What are the substances are present? You can read also that one at a particular point. Okay. Next. This technique is used for testing and purity of the drug sample. So usually I'm telling you about the drug sample because it's the pharmaceutical, we are giving the emphasis of that one. So sample, and also to test the quantity control of the number of substances like cement. See, I told you soil and ores. Okay, so cement, soil, glass, etc. So this is the application of that. Used for the determination of the heat of the reaction. Okay, heat of the reaction is also that is can be determined by this reaction. Specific heat also, and energy change occurring during the melting. how the energy, endothermic, exothermic, endothermic, what are the nature of that one? So that can be also that is determined by this process. So trained in the ligand stability, thermal stability of the ligands. Ligand stability means, you know, that a ligand is the that who can donate its electron to make the bond. Okay, so that is the use of ligand. It is monodendent or bidendent or that polydendent, whatever the type, chelate, whatever the type of ligands are there. So that ligands, thermal stability of the ligands also can be because as it is associated with the ore, I am several times telling you, associated with the ore. So ore is having that ligand type nature is there. So giving the information about the ligands in the coordination sphere. Okay, now the thing is that, okay, so these are the some facts is associated with this that is your DTA. Let's see and understand these things by watching one video also. So we have to understand that how this thing is happening. Just let me share that one. Just a second.
or theory of differential thermal analysis. In differential thermal analysis or DTA, the temperature difference between the test sample and reference material, which is non-reactive and generally is alumina, is followed while the two substances are subjected to identical and controlled heating or cooling. The thermal plot is temperature difference versus the temperature of reference material. If the sample does not undergo any physical or chemical change, then there will be no temperature difference between sample and reference. But a temperature difference will definitely occur if sample undergoes any chemical change. For instance, in an endothermic change such as melting or dehydration of the sample, the temperature of sample will be lower than the reference. On completion of the process, the sample will again show zero difference of temperature as compared with reference. On the other hand, if an exothermic reaction takes place, the sample temperature will be higher than that of the reference material.
Already we have.
If we plot a graph of temperature and time, the temperature of the reference will show a linear increase, while the temperature of the test sample will show hump for the exothermic reaction and decrease for the endothermic reactions. And if we plot a graph of difference of temperature versus temperature of the reference, the graph obtained is in the form of peaks. For endothermic, peak will be in the downward direction, and for exothermic, the peak is in upward. The shape and size of the peak gives a lot of information about the nature of the test sample. Endothermic curve is the physical change, while exothermic is the chemical change. The oxidation reaction gives exothermic curve. The melting or fusion are endothermic. Peak areas and peak heights are used for quantitative analysis. If you like this video, please click on the like button and also subscribe to my channel.
Let's see another thing also, differential that is just a second, thermal analysis. Okay.
Hello everyone. Today we'll look at another technique which we commonly use to understand the construction materials. It's a thermal analysis, right? So in the next few lectures we'll talk about the principles of various techniques which we use, and also we will see application of thermal analysis construction materials. Okay. So, the first question comes to the mind, what is thermal analysis, right? So, basically thermal analysis refers to a group of techniques which study the properties of materials as they change with the temperature. So, the focus is on the temperature. As you are changing the temperature, how the properties are changing, right? For an example, any material, if you heat it up, the temperature goes up, right? But beyond a point, then there might be change in phase. Simple example, ice. For an example, ice will turn into water at 0 degree Celsius, and then that water will evaporate at 100 degree Celsius, right? Another example could be what happens when you coal. If you burn coal, it will be gases coming out of coal, like inflammable gases, right? So, depending on the material, you will see a particular response, right? And that is very unique to a particular material, how it responds to a change in temperature. So, that is the focus of this technique, right? So, thermal analysis is performed to obtain properties, right, such as enthalpy, thermal capacity, mass changes, and the coefficient of heat expansion, right. So, just to keep in mind that whenever we change the temperature, something happens to the material. If we can capture that, it will help us identify a lot of properties, right, behavior of materials. So, a lot of techniques come under this thermal analysis, right. We call it thermal methods. So, and they are used for different purposes, right. It is good to know why we are using a particular technique. For an example, differential thermal analysis, DTA, as it abbreviated as DTA, used for understanding phase changes, reactions, lot of reactions, right. And what we are doing in this technique is we are measuring the temperature difference, differential thermal analysis. Anyway, we will go over each technique, but here I am trying to give you an overview. What are the different techniques, what property do we measure, and where it is used, right. Next is differential scanning calorimetry, DSC, where we are measuring power difference or heat flow, right, the differential thermal power. You can see it can be used to calculate the heat capacity. Also, it can be used to understand the phase changes.
Actually, that is our topic is that only. So today, that our discussion part is that. Okay, so all three things are there. So if you'll see that all three things are covered in this particular unit. So that is your differential. Okay, differential thermal analysis, scanning calorimetry, and a thermometric titration. So this video contains all the things, all the three phases. You have to go through this video once, then I will come to the titration, what is the stepwise process, what to do, what that is everything. Okay.
Various reactions. Next one is thermogravimetric, right, TZ or TGA, where we look at various reactions like where decomposition happens, dehydration, dehydroxylation, oxidation, etc., right. In this technique we measure the change in mass, okay. That is the property we measure in TG. There are a couple of others like thermomechanical analysis, TMA, where we measure deformations. It is used to understand mechanical changes, right, like and expansion. Dynamic mechanical analysis, DMA, is used for measuring moduli. It can be used for polymer to determine the polymer composition, glass transitions, phase changes. These are few applications. Okay. So, but in this course we will focus on DTA, DSC, and TGA, which are commonly used in construction materials. So, starting with the differential thermal analysis, right? First you need to look at the name, differential thermal analysis. Differential is term difference emphasizes an important feature of the technique. Okay. Basically what we are doing, we are measuring the temperature difference between sample and reference. You have a reference along with your sample, and as you are heating your sample and reference together, you measure the difference, temperature difference. That's the key. So you can see sample and reference are in the same cell, right? And you have a thermocouples to measure the temperatures, and finally we measure the temperature difference. Okay. So delta T equals to Ts minus Tr. That's the key. That's what we are measuring. So what is the principle, measurement principle behind DTA? Now we said that we are measuring the temperature difference. So basically if you look at now, let's focus on the left plot. What we are doing here, we have plotted temperature versus time, right? So you have a furnace, for an example, you have a sample and reference. Now you are heating both together. So first look at the furnace temperature. So we have programmed our heating rate such a way that it increases linearly. So you see that solid line shows you how the furnace is heating up, right? Now the reference, you have to make sure you use the reference which is not reactive, right? So that's one of the key features. I have mentioned here alumina, basically alumina, silica, silicon carbide are commonly used reference materials because they don't change with the temperature in the range we are interested in, right? So you see some lag here, but more or less the reference temperature also is increasing in the same rate. Clear? You have this dotted one for reference, right? You can look at the legend also. Now what happens to the sample? That's where we are more interested in, right? So I will just go over a couple of things, but then we'll go in detail. So when something melts, right? So suppose the sample temperature is also increasing, right? When the melting starts, then what happens? The temperature doesn't increase, right? Something is melting, so it will melt, right? So you see there is a flat line here. So that means temperature is constant, right? Because it's a melting, right? But once the melting is over, then you see there is an increase in temperature, right? Clear? Then it comes to next regime. So now if you look at it, now if we plot the temperature difference, what we are doing here, as we said, in differential thermal analysis, we are plotting temperature difference with time. So this is the time axis. So what you see in melting is difference, means we are looking at this difference. This is the difference here, right? Difference between reference and sample, right? So when something is melting, you see the difference is increasing, right? So this thing we are plotting it this way here, right? Once the melting is completed, now you see the difference has decreased, right? So this also tells us that it is an endothermic phenomenon. Endothermic means melting will need heat, right? You are supplying, like you are heating it up, so that heat is being used to melt the material, right? So endothermic peak tells you that something is melting. Depending on the reaction, now further if you increase the temperature, right? So now you are here. In this case you see something different, the temperature is decreasing. When that will happen? Right? It depends on the temperature where you are. Exothermic means then you will release heat. When you release heat, then the temperature difference will reduce, right? It depends on the reaction, the material, what happens as you heat it up. So in this case you see this exothermic peak. Exothermic reaction will lead to increase in temperature of sample, so your difference with reference will reduce, right? So these are some signatures, like in a DTA curve you see these kind of things, right? You will see endothermic peaks, you will see exothermic peaks, so that will tell you what kind of reaction may take place, right? So also important to keep in mind the reference material which is used in DTA analysis, DTA should not react, right? It's so alumina is commonly used reference material to analyze cements, for an example, right. Silicon carbide is another material, right. But as you know, we have to use a material, reference material, which does not change with temperature. Okay. Now we talked about, we are interested in measuring temperature, right. So it is also good, it is important to understand the principle of thermocouples. Thermocouples are used to measure the temperature, and there is something involved in that, right. It is not very easy to measure temperature, you know, we are talking about 1000, 1500, 1600, 1700 degrees Celsius, right. What do you use, what kind of thermocouple? So we will just go over some basics. So basically it relies on a principle that when you join two dissimilar metals, for an example, and now if there is a temperature difference, that will lead to current, thermoelectric current, and by measuring that voltage we are able to measure the temperature. So see, thermocouple is an electric device consisting of two dissimilar electrical conductors, right, forming this electric junctions at different temperatures, right. So you have two different materials, that is very important, and if there is a temperature difference, that will lead to this electromotive force, EMF, or voltage. Once you measure the voltage, we can get an idea about the temperature, right. So thermocouple produces a temperature dependent voltage as a result of thermoelectric effect, right. So based on the temperature difference, you will get the different voltage, and that can be calibrated. So depending on the type of materials you have in a particular thermocouple, you can calibrate it. You can calibrate it means you can calibrate like this, you know, here you have a voltage plotted against temperature for different types of thermocouples, right. So you can calibrate it. So you know at what temperature you get what voltage. So if you know that voltage, you can easily calculate the temperature. This is the characteristic function, okay. And as you see here, voltage can be interpreted to measure temperature. That is what we are doing in thermocouple. So we are measuring the voltage, like measuring, and then using that voltage to calculate the temperature, right. So this voltage basically depends on, you know, there is a relation here. You see voltage depends on the temperature difference, obviously, and also Seebeck coefficients. So Seebeck was the scientist which proposed this theory, Seebeck effect, right. You can go and read about it, but here just briefly just wanted to show you that there is a dependence between voltage and temperature depending on the material. So you see also here is a table where you have different types of thermocouples, type B, type E, type J, K, N, R, S, T, and see notice the conductor combination. It depends what kind of material you are using. In type B you have a platinum 30% rhodium and platinum 6% rhodium, okay. These are the two dissimilar metals we are using, okay, or electric conductor in a sense. Also let us look at the BRS for an example. BRS are commonly used for high temperature measurement. You see what is the temperature range used for BRS, type BRS? You are talking about 1370 to 1700 degrees Celsius. For B, 870 to 1450 degrees Celsius, quite high. So this is the temperature range used if you are want to use these types. So it depends on your requirement, what kind of temperatures you want to measure. If you want to measure low temperatures, then you can use like type E, J, right, for an example, right. So it is very important. So that is the principle of thermocouple, that is what we are measuring in DTA, right. And here you can also look at these we use. So for an example, type J is made of iron and constantan. What is constantan? Is 58% copper, 42% nickel. It gives you composition also. Basically we are talking about two dissimilar electric conductors. Okay. So now let us look at what kind of processes or phenomena can cause this temperature change, right? We want to study a process, so we want to know like what kind of processes can be studied using this technique. As long as there is a heat release or heat absorption, right? For an example, adsorption, we look at the physical properties. So something is getting adsorbed, right? It's typically exothermic reaction. It involves release of heat. So we can measure. Desorption, it's an endothermic, right? Crystal structure change, when crystal structure changes. Typical crystallization, melting, vaporization, sublimation. These are the examples of physical processes, right? Similarly, you may have oxidation, right? What we typically see when you expose materials to oxygen, right? Environment, oxygen is environment, you will have oxidation. Reduction, breakdown reaction. Chemisorption. Chemisorption is different than adsorption in a sense that you have now chemical bonds. Adsorption is not that strong. Adsorption, you do not have chemical bonds. Here you have some chemical bonds. Solid state reactions. These are some physical and chemical processes where you have some heat temperature change. Now let us look at the factors which influence DTA curve, right? Now we know, okay, so we know how to measure the temperature using thermocouples, different processes. So we get a typical curve. Now it's important what are the factors which can influence your DTA curve, right? If you carry out an experiment, it's important to look at that. So there are a lot of instrument factors, obviously, like furnace atmosphere, right? What kind of atmosphere you have in the furnace, right? Suppose you have oxygen, then you may trigger oxidation. If you have a carbon dioxide, you may have carbonation, right? So furnace and atmosphere, furnace size and shape, sample holder material and geometry, heating rate, thermocouple location in sample. These are some instrument factors which can affect your DTA curve. Also, there are sample characteristics. What kind of sample, like what is the particle size, right? If you are looking at the powder, what is the particle size and how it influences your DTA curve, right? That is also important. Thermal conductivity, heat capacity, packing density, how well you have packed your powder, right? For an example, sample amount, 5 milligram versus 10 milligram versus 15 milligram, 20 milligram, right? These are some sample characteristics which will influence your DTA curve, degree of crystallinity. So same thing, now we will go over. So heating rate, for an example, we said like heating rate, right? You are heating the material like sample. Now I can use 5 degrees Celsius per minute versus 10 degrees Celsius per minute versus 15 degrees Celsius per minute. I am heating the sample, but is it going to change, right? That's what we are focusing. So heating rate means, higher heating rate means broader and deeper peaks. We saw that in DTA you get the peaks, right? You may get endothermic peak, exothermic peak, right? Depending on the change. So when you have this increase in the heating rate, means your peak will be broader and deeper. Okay, I think there is one example after this. Sample mass, higher mass means broader and deeper. Similar effect is seen when you increase the sample mass. Okay. Now particle size, how that affects your DTA curve. So everyone is familiar, when you have a smaller particles will tend to react faster rate, right? Faster reaction with smaller particles. You have higher surface area, right? So leads to more delayed peaks with coarser particles. If you have coarser particles, will lead to more delayed peaks. Okay. Also there is the additional distortion if the reference has a totally different particle size, because we are talking about the reference material also. If there is a very much difference between the particle size of a sample and reference, you will see some distortion in the peak. That is what it says. Particle packing, how it affects the DTA curve. See, dense packing implies higher thermal conductivity. If you are packing something densely, that means you have a higher thermal conductivity, right? Whereas loose packing implies more permeability, right? So higher thermal conductivity means might lead to quicker reaction, right? Thus the type of reaction is important. Furnace atmosphere could be important in some cases. For an example, in cement testing, we usually use nitrogen purge atmosphere because we do not want it to react with carbon dioxide for an example. We do not want carbonation to happen. Right? Also we do not want any change, so we use nitrogen rich environment. So these are some important factors you have to always pay attention when you do experiment or you look at the data in literature, right, because these things will change. So I will give you one example. So one of the most celebrated example of the application of DTA, right, to material science is this. Basically it relates to the use of high alumina cement, which in some circumstances led to the weakening and in extreme cases the collapse of concrete structures. So high alumina cement was being used some 30-40 years ago. So at the time there was some issue with that, right. There was, people noticed that it was weakening the structures, also in some cases was leading to collapse. So wanted to know why, particularly with the high alumina cement, right. The problem actually arose because of the conversion. Add water to your calcium aluminate cement, you form this calcium aluminum hydrate CaH10, and it gets converted to C3AS6 and AS3. Okay? So this conversion, right, it leads to loss of strength. Okay? We want to know what is the extent of conversion, right. So in this example, obviously if you look at the DTA, right, this is the now typical DTA curve for calcium aluminate cement, right. So you see this peak, one peak, then this peak, right. This is the DTA curve. So first peak is because of the dehydration of CaH10, right. This is the reaction, right. You are forming now these two phases C3AS6 and AS3. I am using cement chemistry notation. AS3 is, it is written as Al2O3 3H2O. A means Al2O3, H means H2O, C means calcium oxide, C means, okay. So now the second peak is due to dehydration of AS3. This peak is third one is because of the dehydration of C3AS6. This is the temperature axis. Notice x-axis is your temperature, right. Now if you have to get the extent of conversion, simple thing would be you can do y over x plus y, like if you know, right. This is obviously not exact because we are now looking at the peak height. Usually peak height is used when there is there's quite a bit of overlap between the peaks, right. Then it gives you some approximate reasonable value, but just wanted to show you that way they were able to quantify like what is the extent of conversion. So applications of DTA are sample identification, because you can identify samples, it will have its signature, where you are seeing this dehydration for an example, right, because that is dependent on the phase you have, right, it has particular signature. Quantitative analysis, so area under the peak is the representative of mass of phase in sample, right. Also extent of reaction, any extent, what is the degree of reaction we can calculate, okay. These are few applications of DTA, okay.
Okay, so that means we have finished with the differential scanning calorimetry, and now we have to move to the that is your last part of this unit, that is your thermometric titration. Now let's understand what is the thermometric titration and how does it work.
Thermo, like we mean temperature, and metric means measurement. So thermometric means we are going to be measuring temperatures. The principle of this is that when a reaction happens, any reaction, when it happens, there is some enthalpy change associated with that reaction. So there's some enthalpy change involved, whether it's exo or endo. As a result, temperature changes. And when the reaction proceeds, the temperature changes increase. Only until one of the reactant runs out, or you can say one of the reactant becomes the limiting reactant. For example, in today's video we'll be dealing with hydrochloric acid neutralizing sodium hydroxide to produce sodium chloride salt and water, which is enthalpy of neutralization, because the H ions from the acid will be neutralizing the OH ions from the alkali to produce water. That is known as the enthalpy of neutralization. It's an exothermic reaction. Now imagine that I am taking a polystyrene cup and I'm supporting it on a beaker. I have 5 such setups. The beaker is there just to support my polystyrene cup. It's not there to contain the liquids. The polystyrene cup is the container where I will be collecting my acid and my alkali. It's a good insulator, so I am adding alkali over here. Imagine in the first polystyrene cup I am adding 5 centimeter cube of 0.100 mole per decimeter cube sodium hydroxide. In the second cup I am adding more sodium hydroxide, imagine let's say 10 centimeter cube. In the third container I am having 15 centimeter cube of alkali. In the fourth container I have the same concentration, but this time it's 20 centimeter cube of the alkali, and let's say in the fifth container I have 25 centimeter cube of the alkali. Each time I'm going to be measuring the initial temperature, so I'm going to be making a table. Initial temperature / units, final temperature / units, and obviously change in temperature / units, which are degrees Celsius. Hypothetically, my initial temperature was 22.5, 22.1, let's say 22.0, in this range because it's a room temperature. So in the beginning, my initial temperatures were within this range. Now I am adding 15.0 centimeter cube of HCl in each container. This is the same concentration and volume of the same acid. Now obviously we know that in some cases the HCl will react fully, or in some cases the alkali won't be enough to completely neutralize. I measured the temperatures immediately after adding the acid, and you can see on the table the final temperatures. I am not writing the change in temperature on this table because the space wasn't enough, but let's say the final temperatures were these. You can see the final temperatures were increasing, but then did not increase as much. To understand it better, let's make a graph with volume of alkali on the x-axis and the change in temperature / degrees Celsius on the y-axis. The change in temperature became more and more when the alkali was added. But with 20 centimeter cube and 25 centimeter cube alkali, it did not increase as much. When we draw a graph, we see there are 2 straight lines which intersect at a certain point. In the beginning, OH minus ions were the limiting factor because the first few containers did not have a lot of alkali. So OH minus ions were the limiting factor. The heat released and the temperature change depended on the OH minus ions. But when a lot of alkali was there, the OH minus ions were in excess. But the H minus ions were limiting factor. So you can see that in some cases OH minus were limiting and some cases H plus was limiting. But when you see the maximum temperature change, the volume, when the alkali was there with the maximum temperature change, you can see on this graph, the maximum temperature change was obtained with the volume that produces maximum delta T. Why does it produce maximum delta T? Because the reaction reached its fullest point. That is because all the H plus ions were neutralized by the alkali. So all H plus ions moles were neutralized, and that is because complete neutralization occurred of those 15 centimeter cube H plus ions that were added. So 15 centimeter cube of 0.100 mole per decimeter cube HCl was completely neutralized to produce the maximum temperature change. This was achieved only through a graph that had two straight lines which intersected each other to give us the volume, which in my case is around 16.5 or like 17ish. So now let's continue this past paper question. It says you are to determine the enthalpy change of neutralization of hydrochloric acid by aqueous sodium hydroxide. Measure and record. Rinse the plastic cup. Repeat volume of alkali, or you can say FA1 slash centimeter cube comes here.
So that means this
It's
was the
going to be
topic, and now the thing is that the
5,
questions are there.
10.
So you don't have to discuss the questions and all the things. Okay, just a second. Okay, so the thing is that we have completed this portion, that is your differential thermal analysis, scanning calorimetry, and thermometric titrations. Just a second, please. Let's go through again that thermometric titration. Let's understand the things. Another professor video I'm sharing with you.
Now, if I look at the word titration, what actually it means? It is a technique where we are determining the concentration of unknown solution. We all are familiar that when we have done this titration with burette, conical flask, at that time unknown solution or analyte we have taken in a conical flask, and from the burette whose concentration is known, like base which is added in the burette, which reacts with the acid, and we can able to find out the end point or neutralization point of this particular titration by utilizing indicator. Indicator indicates me completion of reaction by change in color. Now, the same titrant which is there in the burette, titer or analyte which is there in a conical flask, the same titration I can able to perform by using thermometric titration. The word thermo defines me change in heat or the heat generated during the titration. So, in thermometric titration, what we are going to find out? We are going to find out the end point by measuring the heat generated during the chemical reaction. This is one of the technique where end point is accurately and precisely we can find out and interpret by finding out the change in temperature by plotting a graph. The enthalpy change, which is most fundamental and universal property of a chemical reaction. So, during observation, temperature change is a natural choice in monitoring the progress of a reaction. Hence, this titration is also termed as enthalpy titration. Looking at the basic principle of this thermometric titration, where like regular titrant, titer, we are going to find out, we are going to add definite quantity of titrant from the burette into the analyte which is kept at adiabatic condition, where we are going to find out the change in temperature by using thermocouple. This end point is nothing but an inflation in a curve generated due to the output obtained as an temperature measuring device. Like if both of them are kept at constant temperature and I will be measuring the change in temperature of the reaction mixture by thermocouple, then the end point I can determine by plotting a graph of temperature versus volume of titrant added from the burette, where this inflation change in temperature, this is the end point of your titration if the reaction is exothermic, and this is the end point if the reaction is endothermic. We are going to find out in detail the thermometric titration curves too. Now, the completion of reaction. During the completion of reaction, it produces molar heat, that is the delta H, which can be measurable by knowing the change in temperature. So, in an ideal system where no loss or no gain of heat due to environmental influences are involved. So, if I want to go in process, I just have to have that there is no loss or gain of heat due to environmental influences are involved in the progress of the reaction. So, reaction itself gives me whether it gives me any absorption or evolution of heat. If it gives me exothermic reaction, then you will get delta H negative, and if delta H is positive, then we can conclude that the reaction is endothermic. Now, if I want to perform this particular thermometric titration, what basic condition I should have to have? Like during volumetric titration, we are following some basic condition that the reaction should not go any byproduct, it should be stable, it should give me same product or balanced equation, reaction should be fast. In the same way, here we will have to follow some basic conditions like reaction must be carried out under adiabatic condition, reaction should be takes place in a single step, and heat of dilution of reaction should be negligible. Heat of dilution of reaction should be negligible. So, these are the basic conditions to follow to perform thermometric titration. This is an instrumental setup of thermometric titration where you are having this block of stylogram where this acts as an insulator. It acts as an insulator. This particular insulated beaker has been kept which contains your analyte. This is an titrant. This particular arrangement allows you from the burette to add a titrant into analyte. This is an motor driven stirrer where mixing the solution of analyte and titrant is possible, and this particular thermistor or thermocouple is attached to Wheatstone bridge network, which is very sensitive to measure the temperature difference of 0.1, 0.2 degrees Celsius during the reaction process. Now, while performing the titration, what specific methodology I need to follow by choosing the analyte, while choosing the particular titrant, while carrying out the reaction, the amount of analyte which I have selected, it should be in such a way that the volume of titrant needed to add during the reaction to measure the change in temperature should not exceed between 1 to 3 ml. The change in temperature during equivalent amount of addition of titrant after every addition, at least there should be change of 0.1 to 0.2 degrees Celsius, and the volume of the titrant delivered per minute, that flow is maintained as 0.1 to 1 ml per minute. So, these are the basic condition that it at least show me a change in temperature with 0.1 to 0.2 degrees Celsius after addition of titrant 0.1 to 1 ml. So, equivalence point should be in this particular range of 1 to 3 ml of particular analyte when it reacts with your titrant. So, keep the concentration of reactant which is there 100 times greater than the reactant to or analyte to avoid the volume correction or to minimize the temperature variation between the sample and the analyte. So, your titrant should be 100 times greater than concentration with respect to your analyte. The thermistor which we are going to able to measure the temperature, it should have to have an accuracy up to 10 to the power minus 4 degrees Celsius. Now, when I am performing this thermometric titration, which factors will affect my titration? Heat losses or gain from outside the system through the vessel, difference in temperature between titrant and titer, as titrant is there in the burette and titer or analyte is there in adiabatic beaker. Evaporative loss from the surface of the fluids when I am mixing or when the stirrer has been utilized, the evaporative loss. The heat of solution when titrant mixed with the analyte. Heat introduced due to the mechanical stirrer. I am applying the stirring process so that the analyte and titrant should be get mixed. Due to that process, due to that mechanical action, does it provide or does it introduce any heat into your solution, and heat produced by the thermistor itself. So, these are the small basic factors which will affect your titration. When I am carrying out thermometric titration, I am taking a titrant of number of moles, specific number of moles. I am taking analyte of definite moles which will produce a product of corresponding mole, and completion of reaction produces molar heat, that is delta H, due to change in temperature. So, this is an ideal presentation of your thermometric titration we can consider, where there are no losses or gain of heat due to environmental influences, and the progress of the reaction is observed as increase in temperature or decrease in temperature. Yes, we will interpret here the titration curves obtained during thermometric titration. Once we have performed the titration, we will have a data of ml of titrant added and the change in temperature. So, we will plot a data change in temperature versus ml of titrant added, and if the reaction is exothermic, then what happens that the temperature increases after every addition of titrant to the analyte, and it will reach to the highest temperature till your analyte is present in the conical flask and it is reacting with your titrant added from the burette. Once whole analyte is utilized, it will show decrease in temperature with excess of addition of reagent or the titrant from the burette. Extrapolation of these straight lines will give me end point of the exothermic titration. Similarly, when I am performing any titration where the data obtained is plotted in the same way as change in temperature versus ml of titrant added, and if it shows me decrease in temperature for every addition of titrant from the burette to analyte, then it will be an pattern of endothermic reaction where decrease in temperature is observed, and this decrease in temperature is observed till my analyte is there in the conical flask, which will react with the titrant from the burette. Once whole analyte is utilized to convert it into product, then excess of addition of titrant from the burette will gives me little bit increase in temperature or it may remains constant. Extrapolation of these straight lines gives me end point of a titration. Now, when I want to interpret the titration curves, sometimes I may get the titration curve of different nature. Now, how it is possible for me to interpret this particular curve obtained after titrating boric acid with strong base like NaOH. I am titrating boric acid with strong base like NaOH. What is happening? This is an titration plot obtained where change in temperature versus volume of titrant added in microliters has been provided to you. Now, the plot is obtained, the nature of the plot you can see clearly in this particular pink color image. Look at each and every point. This point A is the beginning point where it shows little bit decrease and you may think that it will be an endothermic reaction. So, beginning at the beginning temperature is little bit decreased. This line AB is a stress temperature of solution before addition of titrant is point A, and after addition of little bit titrant AB slope is excess of transfer of heat, between solution and surrounding. We can interpret this particular AB line as excess of transfer of heat between solution and surrounding. Now, it is showing increase in temperature gradual from point B to C. So, this is an evolution of heat, exothermic reaction, and at point C where again whole analyte or boric acid has been utilized and excess of addition of NaOH shows me this point C to D little bit down slope as an again decrease in temperature. So, linear extrapolation of this particular graph from CD and from BC, I can find out this end point of a titration at point C. So, this is your delta T, difference in temperature. This particular delta T has been utilized to find out the enthalpy of a reaction. Yes, here I have tried to show you exothermic as well as endothermic reactions simultaneously to find out the progress of reaction and end point during the titration. When these are both of them, we can call it as enthalpograph, where we are finding out the enthalpy change. If enthalpy change is negative, this is an baseline. If enthalpy change is negative, when this particular graph represents you exo and endothermic curves. When enthalpy is negative, delta H is less than 0, means the system is releasing heat. This is called exothermic reaction, and when enthalpy is positive, delta H is greater than 0, the system shows me endothermic reaction. Plot A, upper part, the plot A is for exothermic and plot B is for endothermic reaction, showing starting of the titration and progress of the reaction to find out equivalence point or end point. So, I can find out this B dash as equivalence point, here again B dash as an equivalence point, and delta T, the change in temperature, I can utilize to find out enthalpy of both of these reactions. Hope you have understood how to calculate, how to grab the data from these thermometric curves. So, I can perform this thermometric titration in different types of titration like acid base or neutralization titration, redox titration, complexometric titration, precipitation titration, and miscellaneous methods here defines U titration of fluoride with boric acid, determination of formaldehyde, thermometric titration of water, etc. So, looking at the broad application of this thermometric titration, where I can find out the delta H value. Here further the same type of pattern has been shown with respect to the titration, where I can find out the end point. Here I have tried to show you how to extrapolate the line, and this arrow shows me the end point in both the cases. This is an end point in both the cases, which is very simple to understand. This is strong acid, strong base titration. Again, we are looking forward in detail with respect to strong acid, strong base titration, where our aim is to find out the heat of neutralization of fully dissociated acid with base. So, we have utilized strong acid and strong base. Strong is the word described or attached when dissociation observed is complete dissociation. So, whatever completely dissociated acid and base, when they react, we can find out standard enthalpy of reaction and the standard enthalpy of formation. The reaction is exothermic. The reaction is exothermic as increase in temperature is observed during the process where acid is utilized to form a neutral product like salt and water, and excess of addition of base shows me this part CD, where I can find out by extrapolation of these 2 points the equivalence point. So, this particular information of finding out the standard enthalpy for formation of water, and by knowing for OH minus ions I can easily find out the enthalpy for fully dissociated acid. So, this is an application, an industrial application for interpreting the compounds or the acids and bases which are directly and accurately reacts because of their reaction. Thermometric titration, interpretation of curve with the weak acids like formic acid and citric acid. We have taken an example over here which reacts with the strong base like NaOH. Now, this interpretation of weak acid with strong base by considering formic and citric acid, the curve interpret me that increase in temperature is observed when it is forming, it is giving me a product with respect to reaction of formic acid and NaOH, and when completion of reaction is there, it showed inflation in the temperature. So, this is an end point in case of citric acid and formic acid, weakly dissociated acids. Still we can find out sharp end point due to thermometric titration. When we are performing an titration like complexometric titration where calcium and magnesium, we can titrate with EDTA. This simple titration you might have done with your graduation studies, where you have titrated calcium and magnesium, that is the hard water, with EDTA by utilizing pH 10 buffer and Erichrome black tea indicator, where wine red to blue coloration tells you the completion of reaction. Same titration if I perform with thermometric titration, how it is possible for me to find out the enthalpy or heat of chelation during formation of complex with calcium and magnesium with EDTA. So, separately we can find out their chelation capacity. So, this is a thermometric titration where sodium and magnesium has been utilized to titrate with EDTA. This titration is carried out with a concentration 1 mole per liter, and the amount of the concentration of the titrant which has been utilized is 0.25 moles per liter. Now, when I am performing the titration, increase in temperature is observed when your EDTA reacts with calcium, and it will again show decrease in temperature when excess of addition of your titrant is there, and which will be forming complex with magnesium. Completion of formation of complex with calcium and magnesium, when it is over, then excess of addition of EDTA shows me constant temperature. So, this point B and C we can find out and consider as equivalent point of calcium and equivalent point of magnesium. So, that is the beauty of this titration. I can separately find out the equivalence point of calcium and magnesium, and I can find out the enthalpy change during the titration.
Okay,
Thank you.
that's
Hope
all
you
about
have
that
understood basic
thermometric
principle,
titrations.
difference.
Okay, how the methods is process, how the things is happened, what is the process, how to calculate, all the things is described in this topic. So let's actually the thing is that we have another this unit is covered. Okay, so we have another important area is fundamentals of radioactivity. You know that in MCH-1 we have discussed that is how to that is do the that calculate how to calculate that that radioactive elements that is presence of radioactive elements in MCH-1. So MCH-4 it is actually a technical that is issue, and a very that is hazardous things are generated in this nuclear that is reaction method of reaction radioactivity. So that a topic, as you know, that this topic is something like that. Your just a second, please. Let me share this topic. As you know that this the name of this topic unit 12 is fundamentals of radioactivity. So that means as you know that this is the radioactivity elements and radioactivity nature containing that is topic. Okay, so this is very that carefully we have to handle these things. Okay, so now we have to understand that is that is this topic. What is the objective of this particular unit? So distinguish between radioactivity and stable or non-radioactive substances. That's the first point. Radioactivity and stable and non-radioactive substances. Second objective is to describe the simple laws of radioactivity. That is, what are the laws are associated with this radioactivity areas, its unit and the correction of mass and energy. Third, distinguish between the natural and artificial radioactivity. Okay, what are the natural and artificial radioactivity? Discuss a decay of that is a decay law and a classification of nuclides. So distinguish between chemical and radioactive equilibrium. So describe the nuclear reaction and the preparation of radioisotopes. List various that is of detector to use to measure the radioactivity. Explain the statistical behavior of the radioactivity, and the end point we have to get the objective of this chapter is discuss background correction in radioactivity measurement. So actually the thing is that let's understand what is radioactivity. Okay, let me do that see, this is the thing that as a terminology is radioactivity, so means the term is associated with the that is nuclear particles. So that is your that particles which is associated in a that is nuclear energy and all the things. Just a second, please. Okay, so as the thing is that it is participate in the nuclear particles, means that you know that if basic structure of atom, if you understand, that is atom has two parts. If we that is broadly, if we divided atom, it has two parts, right? One is nucleus and another is outside of the nucleus. Okay, so you know that so many charged particles are present in that particular atom. It is around 17 charged particles are present in that atom, right? So if we say that okay, basic particles are that is your neutron, proton, and electron. Okay, no problem. In an atom, lots of around 17 charged, that is cation, meson, positron. That 17 charged particles are present. So out of that, if we discuss about that, we are discussing about that nucleus as well as outside of the nucleus. Inside the nucleus, major two charged particles are present. One is your neutron, second is your proton, and outside the nucleus only one charge particle means one major charge particle is present, that is your electron. If we discuss about this radioactivity, this is that name contains with the nuclear particles. Nuclear particles means the particles which is present inside the nucleus. So what are the particles are present inside the nucleus? That is your major particles. We are discussing with the major particles. That is your proton as well as neutron. So this proton means Z. What you can say the proton, number of protons Z, and the neutron N are often called nucleons. So to all together, if we say proton and a neutron together called nucleons. Nucleons. The only accepting that being is highlighted hydrogen nucleus. So if you see that hydrogen has only one proton, there is no neutron present in case of hydrogen, right? Hydrogen is it has zero neutron. I'm telling about the hydrogen. So that is that only exception being is lightest of the hydrogen nucleus, which consists of single proton only. So that is only. I am telling you the basic structure of atom right now. So this is that. From that point, we will connect to the radioactivity. Okay. So the proton only. These remain bound inside the highly dense. So these things these particular things is remain bound inside the highly dense nucleus by strong nuclear force of attraction, which is actually the dimension is 10 to the minus 13 to centimeter to 10 to the minus 15 meter, around that form. So the sum of this proton and a neutron in a nucleus is referred to as the mass number. As you know that is neutron and proton altogether called as the mass numbers. So that is represented A. So all the atoms whose nuclei contains the same number of protons have similar chemical properties. If have same number of protons, if that is what you say, the protons have the same number of protons, people say that usually if I'll give the example of protium, deuterium and tritium, this is the isotopes of hydrogen. So protium, deuterium and tritium, we are not discussing about that electron. We are discussing that protium, one proton is there, zero neutron is there. So in the that is deuterium, one proton is there, one neutron is there. In the tritium, one proton is there, two neutrons are there. So always in the three particular atoms, that is isotopes of hydrogen, that is protium, deuterium and tritium, all having the that single proton. Only the difference in case of that is your mass number. Why the mass number is here is 1, 2, 3, because one proton is there. As you know that mass number is that number of proton plus number of neutron. So in case of protium, only one that is proton is there, zero neutron. So altogether one is there. So mass number is 1. In case of deuterium, one proton is there, one neutron is there. So mass number is 2. Atom mass number is 2, and in case of tritium, mass number is 3, because that one proton is there, two neutrons are there. Okay. So what I mean to say, if the number of a proton that is in any particles, if the number of protons are same, always same, so their properties will remain same. So that is the clear statement. So chemical properties is real. That is chemical properties will be same. Chemical properties, I'm telling you, not physical properties, because physical properties will be different. Okay, because mass will be changed. The sum of the protons and neutrons in the nucleus is referred to as the mass number. All the atoms whose nuclei contains the same number of proton have similar chemical properties. Okay, similar chemical properties. I'm not telling about the physical properties. Similar properties. So, but atoms of the same element may have different numbers of neutrons, and therefore different A values will be there. So, as I said, as I told you, as I gave you the example of that protium, deuterium, and tritium. So, number of that is neutron are different. So that's why that means that is your mass number is different. Maybe different. Okay. But atom that have the same element may have the different number of neutrons. Okay, so these are different of A values. Atoms having the same Z and a different A values are called isotope. I told you the isotopes. So what are the isotopes? I gave you the example of that isotopes of hydrogen, that is protium, deuterium, tritium. So that is what are the number of mass and all the things. But the thing is that how it is connected with that. My point is, we are discussing how it is connected with that. That is radioactivity nature. Okay, let's go to that one. So that is isotopes. Each isotope has fixed abundance in nature with few exceptions. The relative abundance of any isotopes is called the isotopic abundance. Okay, so each element has two types of isotopes: naturally abundant stable isotopes and unstable radioactive isotopes. So see that now the thing is that each element has two types of isotopes. Okay, two types of isotopes. So that is, if we say that one may be natural stable isotopes and one will be radioactive isotopes. What is element has two types of isotope. One is naturally occurred isotopes, that is stable isotopes, and one is radioactive isotopes, which disintegrate spontaneously and eventually become the stable isotopes of some elements. Okay, the radioisotopes decay by emitting elementary that is particles such as alpha, beta, gamma, that is electromagnetic radiations. So this is that is behavior with the electromagnetic radiations because of their due to their alpha, beta, gamma, that delta nature of that particular that alpha rays and gamma rays by that undergoing fission breaking down the small nuclear parts. So these isotopes are some cases occurs naturally, such as K40, D2, C13. D2 means deuterium. Okay, carbon 13, 14, there is carbon, potassium having 40 and 41 as there. So deuterium is protium is there, but but are often artificial and man-made, such as the cobalt 60, cesium 137, zinc 65, then polonium that is 239. So these are the artificial isotopes which consider as the radioactive elements. Okay, so now the why radioactives, what is the nature behind this, why the radioactives essentially, why it is known as the radioactives. Okay, the ratio of neutron to proton is often used to an indicator of the stability of a nucleus. So stability of a nucleus gives the ratio of neutron and that is proton. If atomic number Z of all stable nuclei are plotted as the function of the number of neutrons present in the nuclei of plot shown figure 2, this is the figure 1.2, sorry 12.1 is often. So if what is that, if the that is see that if the atomic number Z of all stable nuclei are plotted as the function of the number of neutrons, number of in the nuclei, a plot, this is the plot. Okay, plot of number of neutrons versus number of protons in the stable nuclei. See, this is one stable nuclei where that is you can see, just a second. Where you can see that the number of protons are there and the number of neutrons are here. So if Z is equal to N, so Z is equal to N means beta minus, this is beta minus unstable and beta plus unstable. Beta means beta, that is when you bombarded this alpha particles, alpha ray. So that is a radiation. So beta radiation will be there. So that is beta minus unstable, beta plus unstable, then alpha decay will start. Okay, now that graph is going in the straight line, but then unstable particles are moving, means going to the downwards. So that is what you say that is radioactive nature. Okay. So these are the things that you will see that a variation of N by Z, neutron versus atomic number ratio with the increasing Z. So if we consider here H2, you will see the table 12.1. H2 means hydrogen, that is 2 means your deuterium condition is that Z is equal to 1 means atomic number 1, then a neutron which is equal to 1 and N by Z is equal to 1 means ratio proportion is equal to 1. So here neon 20, 10, 10, 1 is the that ratio. So that is calcium 40, 20, 20, 40 is that. So always if you see zinc 30, 34, 1.13 is that is point. Okay. So if you see that in this case also there are some stable pair of nuclides with odd Z and mass number odd Z means you will see that is your greater than 1. So if it's zinc, then Z minus, Sn, stannous, and neodyne and mercury is there. So you will see that 1.13, 1.25, 1.40 value is there. But in the first three case, hydrogen, then neon and calcium, that is 1:1 is the ratio. Okay. So in this case, what will happen? The chances of the radioactiveness will be more in case of this particular, those having the more number of value of this one. Okay. Z is equal to even. So even, then odd will be Z. The classification of, if that even is Z, N is equal to even. So A plus is equal to even. The number of nuclide 165, helium 4, oxygen 16. These are the examples of that one. Okay. So this will come even, odd, then odd will be there 55, oxygen 17, manganese that is 25, barium that is 137, then lead is equal to 0, odd, even, odd 50, so lithium like this. So these are the classification. Okay. So then that will come down. So radio analytical methods. Following a generalization can be made on the basis of the data presented in 12.2. So for even A and even Z and even N, largest number of stable nuclides are exist. Okay. So even, all are even. So in this case, it will go down even and even. So largest number of stable nuclides are there, 165. Okay. So for odd nuclides, and therefore approximately if nuclides are odd is given there, that is in this case approximately same number of stable nuclides are there. So okay. So for even A with odd Z, even A with odd Z, even A, it will come down to the third point, even N, even A, odd Z. Okay. Okay, even A or Z. Okay, fourth one, odd, even. If that is point, it will come down to this situation. So for even A and with odd Z, only odd N will be there. So only few stable nuclides are found. That is 2 H plus in the number, only 5 stable. So these are the on basis of this generalization of basis of these generalization points. So following inferences can be made. Nuclear force between two nucleons are independent. So when two nucleons are there, so that force of that is attraction, whatever there, force of attraction is there. So that is independent of whether the nucleons are protons or neutrons. So whatever may be the particles, that they are independent. If the nuclear stability is more, then if Z and Z or N are even, the decrease in that is when the either Z and both are the value of that nuclear force will be decreases. So if the value of nuclear force when decreases, so what will happen? The nuclear force will means always stability depending upon the less amount of energy. Okay, when the value of energy is decreases, so that is means less amount of energy will be associated with the that is any that is repulsive value and all the things, less amount of energy will be that developed in that case. So that means more in the stable format. So this is the things that when the unstable is there, so that means if will go to that particular point, if that radiation point, see that a beta minus unstable, beta plus unstable, because this is the that graph which is in straight line, that is going on that is stable format. But when it go away from the stable format, that is the energy level is this means that is scattering of energy level. So in this case, when the scattering of energy level arises, so thing is that so that radioactivity nature will be generated. So think we from that point of view, radioactivity that is nature will be analyzed. Okay, will come down. Okay, discovery of radioactivity. So these are the scientists that is Roentgen is on the X-ray analysis. There he has that Becquerel, Roentgen, and Madame Curie. That is Sir Curie and Madame Curie, both are there also. They are all are associated with this particular the discovery of what is radioactivity nature. Laws of radioactivity. So, what the rate of disintegration of radionuclide at any time is directly proportional to the number of atoms present at that time. Okay. So, this is minus is the sign symbol. This is not negative value. It is the sign symbol. So, d by n by dt is equal to lambda n. So, where n is the number of radioactive atoms of a specific radionuclide present at the time of T, and lambda is the nuclear decay constant. Okay, lambda is the nuclear decay constant, a characteristic of that property of the radionuclide. So this minus sign, see, that is minus sign indicates the decay results in a decreasing in number of atoms. So this is not the mathematical thing. This is the just a second, please. Just a second. Okay, so these are the things, law of radioactivity, how the law will be applied, and all the things we will discuss tomorrow, that is tomorrow class. So hope all of you have gone through this video and all the things. So you just continue with your that is paper, and all the best for the assignment and all the things. Okay, thank you very much.